Hello everyone, today I'll be talking about Elixir, a language that challenges a lot of the assumptions we carry from traditional programming. The subtitle of this presentation asks, what if the way we think about errors is completely backwards? And by the end of this, I hope that question makes a lot more sense to you, so let's get started. To understand Elixir, we need to go back all the way to 1986. That's when Ericsson, the telecom giant, created a language called Erlang. Their goal was brutally practical: build telephone switches that could handle 99.999% uptime. That's roughly 5 minutes of downtime per year. They weren't doing this for fun. Phone calls cannot drop, systems cannot crash, and Erlang was engineered from the ground up around that constraint. Fast forward to 2011, Jose William, a member of the Ruby on Rails core team, created Elixir. His goal was to keep everything that makes Erlang brilliant: the concurrency model, the fault tolerance, the beam virtual machine, but wrap in a cleaner, more modern syntax that developers could actually enjoy writing. Ruby's expressiveness meets Erlang's reliability. By 2014 and beyond, the ecosystem took off. The Phoenix web framework launched, and companies like Discord, Pinterest, and WhatsApp started adopting Elixir at scale. The key design philosophy is this: Elixir is not just on Erlang's VM, it is a deliberate choice about being there. William chose reliability and concurrency over novelty, and that choice shapes everything we're about to discuss. So, what problem is Elixir actually solving? Three big ones. First, traditional concurrency is hard. When you use threads with shared memory, which is what most languages do, you introduce locks, deadlocks, and race conditions. These are notoriously difficult bugs. They're often non-deterministic, meaning they show up only sometimes under very specific timing conditions. Second, distributed systems need resilience. Networks fail, servers crash. A robust system needs to self-heal without a human waking up at 3 a.m. to restart a process. Third, scale demands a new model. You simply cannot manage millions of concurrent connections using a thread per request approach. The math doesn't work. Now look at the numbers on this slide. Discord served over 5 million concurrent users using Elixir. Pinterest handles over 2 billion daily requests. Phoenix servers can handle 2 million concurrent connections on a single machine. And here's one thing that really stands out to me. WhatsApp was handling 2 million concurrent users on a single server back in 2012 with a tiny team, and that is the power of building on the right foundation. Now let's get into the language itself, starting with pattern matching, one of Elixir's most distinctive features. In most languages, control flow is handled with if-else chains or switch statements. Elixir makes pattern matching the primary mechanism. Look at the factorial example on this slide. Instead of writing if n double equals 0, return 1, we write two separate function definitions, one that handles the case when n is 0 and one for any other value. The runtime picks the right one by matching the pattern. This isn't just syntax sugar, it's a semantic shift. When you pattern match, you're forced to think about every possible shape of data your function might receive. Missing a case, the compiler warns you. In Python, an incomplete if-else chain just falls through silently. In Elixir, the language catches that for you. The guards, like in the third example, when age greater than equal 18, is a layer of additional constraint on top of structural matching. And the case expression with exhaustiveness checking means if your data ever hits a shape you did not account for, the system tells you that immediately. Pattern matching is not just about cleaner code, it is also about building in correctness from the start. Next is immutability. In Elixir, once data is created, it cannot be changed, ever. Look at the code on this slide. When we do list equals, we're not modifying the original list, we're creating a new list and binding the variable name to it. The original data still exists unchanged. Now, why does this matter for concurrency? Imagine if process A and process B both reference to the same piece of data. In a mutable language, process A might change that data while process B is still reading it, and that is a race condition. In Elixir, that scenario is structurally impossible. Neither processes can modify the data, and they both get a safe, stable reference to the original. This is the distinction between rebinding and mutation. Elixir allows you to use a variable name, but it never lets you change the underlying data in place. The practical result: the entire categories of concurrency bugs simply do not exist in Elixir. Race conditions, deadlocks caused by shared state, data corruption, all of them gone. Let's talk about the pipe operator. This is one of those features that sounds trivial but genuinely changes how you write code. Look at the left side of this slide. Nested function calls stacking inside each other. Read from inside out. Now look at the right side with pipes. The exact same operations written left to right, top to bottom. It's the way you actually think about data flowing through transformations. The pipe operator takes the result of the left side and passes it as the first argument to the right side. That's it. But the effect on readability is enormous. The real-world example at the bottom, filtering, mapping, reducing, is a complete data processing pipeline that reads like plain English. Take the data, keep only the valid entries, and transform each one, sum them up, and then print the total. Elixir's syntax choices consistently push you towards writing code that reflects your intent and not just the mechanics of execution. Elixir is dynamically typed, but that does not mean it's loosely typed. The slide shows protocols. Elixir's answer to interfaces and polymorphism. You define a protocol like printable, for example, and then you provide implementations for different data types. Strings print one way, list prints other way. The big difference from something like Java interfaces, in Java, a type must declare that it implements an interface at the time it's created, but in Elixir, you can add a protocol implementation to any type anytime, and even types you didn't write. This is called retroactive polymorphism, and it gives you enormous flexibility. For static analysis, Elixir has dialyzer and type specs. You can annotate your functions with expected types, and dialyzer will analyze your code base at compile time to catch type errors without making the language statically typed. You get the flexibility of dynamic typing and the safety of static analysis, toggled by how much you invest in annotations. Elixir's data structures are worth a quick tour because each one reflects a deliberate semantic choice. Atoms are constants that are their own name. They're used everywhere for signaling state and intent. No string comparison overhead, and they're self-documenting. Tuples are a pervasive convention in Elixir. When a function returns a tuple, the shape of the tuple is the contract. You know at a glance whether an operation succeeded or failed and what came back. Lists are linked list optimized for the recursive head-tail decomposition pattern you saw in pattern matching, which is perfect for functional style iteration. Maps are key value stored for domain objects, which are clean, readable, and document-like. The example that you see over here, email refers to alice@ex.com, tells you exactly what you're working with. Every data structure in Elixir is chosen to support a certain style of thinking. In Elixir, functions are values. You can pass them as arguments, return them from other functions, store them in variables, and compose them together. The slide shows a function called applyTwice that takes a function and a value, applies the function to the value, and then applies it again. No special machinery, and it just works. The double lambda gets passed in, applied twice to 50, and we get 20. The enum library is built entirely on this principle. Enum.filter, enum.map, enum.reduce are all higher order functions that take a function as an argument and apply it to a collection. The pipeline at the bottom of the slide demonstrates the combination of pipes and higher order functions. Filter for even numbers, double each one, and then sum the results. That's a complete data processing pipeline in 3 lines, and it reads naturally from top to bottom. Higher order function replace loops entirely. Elixir has no for or while loops, and they enable levels of abstraction that inheritance hierarchies cannot match. Since there are no loops, recursion does all the heavy lifting, and this is where tail call optimization or TCO becomes critical. In a naive recursive function, every call adds a frame to the call stack. You call it deep enough and you get a stack overflow. TCO solves this. When the recursive call is the very last thing a function does, a tail call, the Beam VM reuses the current stack frame instead of adding a new one. The recursion effectively becomes a loop under the hood with constant memory usage. The countdown function on the slide can count from 1 billion to 0 without blowing the stack. Process all can handle a list of any length, same guarantee. And Elixir stream module takes this further. Lazy infinite sequence that compute values on demand. The function generates an infinite repeating sequence, and you just take as many values as you need. The trade-off is a mental model shift. If you're used to for loops, recursion takes some time to adjust, but once you get it, you gain safety and infinite stream processing as a free bonus. Combining immutability with pure function gives you something incredibly valuable, which is predictability. A pure function has no side effects, same input, same output every single time. So, for example, calculate tax 100 will always return 10. You can test it with a single line, no mocking, no setup, and no database state to manage. Side effects like logging or writing to a file still exist in Elixir, but they're explicit and isolated, not hidden inside functions that appear pure. The code on the right shows a function that is explicitly labeled its side effect. It logs, then transforms. The side effect is visible, not buried. The result: pure functions are trivially testable, easy to reason about, and safe to run in parallel. This is the foundation that makes Elixir's concurrency model work. Now we get to Elixir's killer feature, the actor model. Look at the code on this slide. We spawn a process, not an operating system thread, a lightweight process managed by the Beam VM. We send it a message, it receives that message and responds. 3 lines of code. Here's why this is remarkable. Beam processes weigh about 2 kilobytes each, and an OS thread weighs about 1 megabyte. That's 500 times lighter. On a modern machine, you can run millions of concurrent processes simultaneously. And critically, each process is completely isolated. Processes don't share memory, they communicate only by passing messages. If one process crashes, it has zero effect on the others. They don't even know it happened. The analogy I love for this is like texting versus sharing a Google Doc. With shared memory, Google Doc mode, everyone edits the same thing and one person's mistake corrupts everyone's work. With message passing, the texting mode, each person has their own copy and you only exchange information deliberately by choice. That means no threads, no locks, no shared memories, no race condition. This is Elixir's answer to concurrency. The actor model enables something even more powerful: fault tolerance through supervision. The philosophy is called let it crash, and it sounds reckless unless you understand it. The idea is, instead of wrapping every function in try-catch blocks and hoping you anticipated every possible failure, you let processes fail freely and build a supervisor that watches them and automatically restarts any that crash. A fresh, restarted process in a clean, known good state is more reliable than a process that's been running for 6 months, accumulating invisible corruption. That is the insight. Elixir's OTP framework provides 3 supervision strategies: one for all, that means only restart the process that crashed, good when processes are independent. Second, one for all. If one crashes, restart everything. This is when processes depend on each other and a partial restart would leave things inconsistent. And the third one is rest for one. Restart the failed process and everything started after it for ordered dependency chains. The historical proof: Erlang-based telecom systems achieved 99.999999% uptime, which is 9 nines, and that works out to about 31 milliseconds of downtime per year. Let it crash isn't giving up on reliability, it's achieving it through a completely different strategy: structured recovery instead of exhaustive prevention. Let's see this in action with a real example: concurrent HTTP requests. The code on this slide fetches a list of URLs in parallel, and for each URL, it spawns an async task, a lightweight process that fetches and processes the response. Then it waits for all of them to finish and collects the result. The performance difference is dramatic. If each request takes 200 milliseconds, doing them sequentially take 2 full seconds for 10 URLs, and doing them concurrently, about 200 milliseconds total, the time of the slowest single request. Compare this to other languages. JavaScript uses async with a single-threaded event loop, concurrency without true parallelism. Python's global interpreter lock limits true parallelism even on multi-core machines, but Elixir gives you true parallel processes with built-in fault isolation. Each task is isolated, so if one URL fetch fails, it doesn't take down the others. This is what makes Elixir compelling for real-time systems, APIs, and anything that needs to handle lots of things happening at once. Much of what makes Elixir work comes from its runtime, the Beam virtual machine. Beam was built in 1986 for telecom systems, and it has been battle-tested for nearly 40 years across some of the most demanding reliability requirements in existence. 4 capabilities stand out: Preemptive scheduling. The beam guarantees fair CPU time to all processes, which means no single process can hog the CPU and starve others. Second one, per process garbage collection. Each process has its own garbage collector, meaning there are no stop the world pauses that freeze your entire application. Third, hot code reloading. You can update running code without stopping the system. Zero downtime deployments are a native feature. And fourth and final, built-in distribution. Connect multiple Beam nodes across a network and they work transparently together. Look at the code snippet. Spawning a process on a remote machine uses identical syntax to spawn one locally. The abstraction is seamless. Elixir also supports metaprogramming, which is code that generates code at compile time through a feature called macros. This means library authors can create syntax that feels as natural as built-in language constructs. You can extend Elixir from within Elixir, but the community's wisdom on this is important. Don't write a macro when a function will do. Overusing macros makes code difficult to debug and understand. Macros are a powerful tool best used sparingly by library authors who know exactly what they're building. To tie it all together, let's look at a real-world example, a chat system built with GenServer, Elixir's general-purpose process wrapper. The code shows a chat room module. Each chat room is a separate GenServer process with its own isolated state. Users send messages via broadcast message. GenServer handles both case messages, fire and forget, and call messages request response through dedicated callback functions. The architecture is elegant. One process per chat room, one process per user connection. Messages flow through the actor model. If a room's process crashes, maybe someone sent malformed data, the supervisor restarts it instantly from a clean slate. Users reconnect automatically. This isn't hypothetical. Discord migrated from Python to Elixir and cut message latency by 10x. Pinterest reduced their notification service from over 200 servers to about 4 servers. Phoenix has benchmarked at 2 million concurrent WebSocket connections on a single machine. Looking at the comparison table, Elixir occupies a genuinely unique position in the language landscape. Go has Go routines for concurrency, but fault tolerance is manual. Rust has strong safety guarantees through ownership, but distribution requires external libraries. Python is easy to learn, but the GIL limits true parallelism, and there's no built-in fault tolerance. Elixir is the only language where concurrency and fault tolerance are not features you add, they are the default way of thinking. Every component is a process, every interaction is a message. You don't opt into resilience, you have to actively work to avoid it. The observation I want to leave you with from this slide, in most languages, concurrency is a special concern requiring extra framework and careful design, but in Elixir, it's just how things work. So no language is perfect and Elixir is no exception, so let's be honest about both sides. Where Elixir excels, distributed fault-tolerant systems, real-time web applications, APIs handling massive concurrent load, IoT infrastructure, data pipelines, anywhere you need reliability and concurrency baked in. Where Elixir struggles, CPU-intensive computation, I think Rust or C++ will outperform it significantly. While its ecosystem is growing, it is still smaller than Python's or JavaScript's. For developers coming from imperative languages, the functional mindset takes real adjustments. It's also garbage collected, so it's not suitable for hard real-time latency requirements. And it has essentially no mature machine learning libraries. You'd need to interoperate with Python for that. So the honest answer is Elixir is a specialist language. For the right problems, it is unmatched, and for others, it is the wrong tool. Knowing when to reach for it is as important as knowing how to use it. So what's the takeaway? Programming language design is about choices and trade-offs. Elixir chooses concurrency, fault tolerance, and developer experience, and accepted that it wouldn't be the fastest at raw computation or the most popular for machine learning. For building reliable systems that handle millions of concurrent users, self-heal from failures, and scale across distributed infrastructure, that is exactly the right call. And the let it crash philosophy isn't pessimism, the actor model isn't just clever theory, and the Beam VM isn't just historical trivia. Together, they form a coherent approach to a genuinely hard problem. How do you build systems that stay up no matter what? And Elixir's answer is worth studying, not just for the language itself, but for the thinking behind it, because how a language is designed shapes how you think as a programmer. Thank you.